So let's start. So this is the first half of the talk, which is Vulkan on Android gotchas, or the process of porting Roblox to Vulkan on Android. Really brief, my name is Arseny Kapoulkine. I work at Roblox. I'm a technical director there. I was not the only person working on the Vulkan port, but I helped to however I could. So what is Roblox? If you have kids, you probably know what Roblox is, or maybe they know and you don't. So this is an online multiplayer game creation platform. We provide you the engine, the tool set, we host the servers for you, and then you build games on our platform. And when I say you, I mostly mean people who are maybe college students, maybe are high school students. They create games, and then other kids of all ages, how we like to call them, play these games. All of this is user-generated content, so we don't actually make games. Users do it for us, which is awesome. We are on a lot of different platforms, and we have a lot of users. And across all of these different platforms, we use a lot of different APIs. So this is an example of one of the top games on Roblox. It's called Jailbreak. It's made by two college students. One wrote pretty much all the code, one built the entire game. This is roughly how the game looks. You can see it's a bit simplistic. It uses a simple art style, has a lot of UI, has some characters in them. Please don't punch me. Okay. This is one of the top games, and this game is pretty big. So it hit 130K concurrent users in February 2018, and I think they are even higher a bit now. So this is the kind of content we want our users to create on the platform. Now, why Vulkan? So we support a lot of platforms, and on each platform there are unique performance challenges. We like the content on our platform to work across the board on each hardware platform that we run on, right, and to work fast. And sometimes it works out for us, sometimes it doesn't. We have to do a lot of optimizations to make it possible. On Android specifically, performance is problematic. There are a lot of hardware issues, like there's thermal throttling, etc. But also you are stuck with OpenGL. You're stuck with slow drivers that are much slower than drivers of some other vendors potentially on Android. And the support for modern API features is kinda not there frequently. And by modern, I sometimes means mundane things like uniform buffers don't always work well, things like that. So we kinda want to push the content forward and the performance forward. And when we saw Vulkan, we thought, wow, this is gonna be awesome for us. We have a lot of experience working with different graphics APIs, and specifically before Vulkan, we actually ported to Metal on iOS and Mac, and we saw very substantial performance gains there, and the process wasn't very problematic for us because when we work with these high-level APIs, we sort of know how the driver works and what it actually is doing for us. So when we are told, well, the driver doesn't do this thing for you, you should do it ourselves, our response is, all right, great, let's do it. And we support a lot of different APIs, right? So just one more didn't seem like it would be a problem. And I mean, if you look at OpenGL compared to Vulkan, the Vulkan is so much slimmer as an API, and things are so much more explicit that the driver's gotta be rock solid, right? Like, I mean, it is hard to imagine that an API so simple could have a lot of bugs. So we were really hoping that this would be great for us. It's, by the way, a Roblox tradition to have a quote in every presentation. So this is my quote. So spoiler alert, there is a happy ending, or rather, not every single character dies at the end. So let's go a bit into the details of what we have seen. So shaders, there was a great talk just now in this room that described the process of using HLSL in Vulkan. So we have our shaders written in HLSL, of course, and we don't want to fork the shaders. We don't want to rewrite them. We want to use them as is with all the HLSL details. We do ship our toolchain, our shader codebase rather right now on OpenGL. So how do we do that? There's a library that is used by the witness that we have heavily contributed to called the shell cell parser, which did the thing that Mateusz told you should not really be doing, which is a AST to AST translation, or rather this is an shell cell parser that gives us the AST, and then the AST is converted to GLSL code. And then we have GLSL optimizer that Unity used to use at the end of the pipeline to make the shaders simpler, to keep the load times of the shaders faster, and to have a bit more predictable performance. We don't want to be relying on the driver based on past experience. Sometimes driver doesn't do it well to optimize everything in our shader for us. So we want to give a reasonably fast shader to the driver and then hope the driver takes it from there. So at the time when we were porting, the HLSL efforts in Vulkan were very early. They were not ready for production. So what we did was a sensible thing. I mean, you can take GLSL and just pipe it through GLSlang to get SPRV, right? Pretty simple. The problem that we hit is that some things that are valid in Vulkan and valid in HLSL, for example, passing textures or other sampler objects to a function as an argument, did not work at all on one of the drivers that we had to support. Like the shader compiler would just refuse to compile it. So we had to work around this. Working around this means inlining everything. Well, I mean, we have GLSL optimizer, right? So let's get it back. The issue here, though, is that GLSL optimizer does not actually support GLES 3 or GLS 3 compatible shaders. It does not support uniform buffers. Vulkan only supports uniform buffers. Well, I mean, we are software engineers. We know what to do. A bit of regular expression magic. Basically, what we do is when we generate GLSL normally, we don't use free-form uniform buffers anyway because of a lot of driver bugs on GL drivers with them. We convert each uniform buffer to a vector 4 array. So then it's easy to say, well, this is a uniform vector 4 array. Let's make it a C buffer. And the good news is this worked. So on Android, there are 4 major GPU vendors. There is ARM, Qualcomm, NVIDIA, PowerVR. The shaders that we generated with this process worked on all of them, which is great. The not so great part is that we kind of want to stop using the HLSL parser library because we don't like to write HLSL parsers. Some of our future prototypes that try to improve the quality of rendering on Roblox use DX11 features, and HLSL parser is fundamentally a DX9 HLSL parser. It does not support the texture 2D objects and whatnot. So what we want to do is we want to move to, roughly speaking, the pipeline that was just described in the talk before. So use GLSlang. We aren't planning on supporting DXC soon because it's not clear if it's right now for us if it's better. But yeah, so GLSlang, SPRV-opt to get the shader size down. One big thing that SPRV-opt seems to also do for us is to reduce the probability of the driver not consuming our shader, because we have hit some cases where if you're using some like structures or whatever, some drivers just don't support everything that you could do with them, and SPRV-opt cleans a lot of this up for us. We also, in the new pipeline, we stripped the debug info. Turns out some drivers actually care about some names of some things that you put in the shader that are supposed to only be there for debug info. So we have to strip this out. One other thing I want to mention is, so all of these tools, they are in development, essentially, right? We contributed several patches to SPRV-opt, and it's kind of a moving target. So what sometimes happens is on a complicated shader, the result of SPRV-opt could be invalid SPRV. So it's super crucial that the end of your pipeline is actually not just SPRV-opt, but SPRV-val as well, which is the SPRV validator. So make sure offline that you aren't generating SPRV that you will then feed into the driver, and then you'll have to enable validation layers to actually catch this. You can catch this earlier. So the reason why this slide says future is we have not shipped this yet. The reason why we have not shipped this yet is the output SPRV doesn't work with all the drivers yet. The problem is that the drivers were mostly tested on the output of GLSlang when consuming GLSL as an input, so they just aren't ready necessarily on Android for some things. So we're working through this problem. We think this is solvable via SPIR-V transformation. Like, since we clearly can compile our HLSL shaders via one pipeline to work in SPIR-V across all vendors, it must be possible for us to do the same with another pipeline. But we are not fully ready yet. Right now, this pipeline for us works without bugs on 2 out of 4 vendors. So work in progress, this is one of what we want to move forward towards. But we did not ship with this, and I'm glad we didn't. All right, now let's talk a bit about the C++ side. So this is, obviously we have a rendering abstraction. I mean, everybody has one. This is roughly how ours look. It's a bit odd, like it's not any one API in particular. It has semblances of Metal. You can see that we explicitly say begin pass, end pass, but there's no pass object that we have. You just pass in the frame buffer that you want to render into, etc. And then you can bind programs, buffers, textures, etc. One interesting thing that we have not seen other people do is our resource binding are across stages. So we only have one namespace for buffers, and if you bind the buffer to the slot 0, it's both vertex slot and fragment slot and compute slot and geometry shader slot and whatever, however many shader stages you have, which actually helped us significantly during the Vulkan port. But otherwise, this is more or less how you would expect an API to work. It was born when we were only supporting GL and DX9 and then slowly evolved. So a lot of things that we do are not particularly intelligent. I mean, a lot of other ports do that as well. So we lazy create and cache everything that we need. We do have a frame buffer abstraction, but it's not quite the same as Vulkan's frame buffer. So we lazily cache and create that. We create render passes lazily. I don't know what else. Oh, pipeline states, right, so render passes, pipeline states, et cetera, et cetera, et cetera. Like anything that is not in our API, there's a hash map for it. Hash maps are fast, turns out. So the thing that we have to do, though, is we have to serialize the pipeline cache to disk, because if you aren't doing that, then the lazy creation of pipeline state objects will hurt you a lot in subsequent runs of the app. And right now we have minor hitches in the first run through the app, but we actually don't have that many PSOs, so it's not that bad. We have essentially what sort of looks like the DX11 style binding model, right? There are named bindings or other numbered bindings. We just implement this using dynamic descriptor sets. So we allocate descriptor sets relatively frequently. We update them, we bind them. And there's a limit of 4,096 memory allocations on Vulkan on a lot of drivers. So you cannot allocate more. So you have to suballocate memory if you have app that's complicated to any degree. Today, I would tell you, and I am telling you, just go use this Vulkan memory allocator library. AMD developed it and open sourced it. You could just plug it in. It should work on Android. When we started, it wasn't there, so we wrote our own. But this is not, we don't have that many memory allocations, we don't suffer that much from fragmentation, so we didn't really see any big problems with that. So now some things that we do that I have seen other people do in Vulkan or DX12 that you should not be doing and we didn't do, and we are happy that we didn't do it. So first, we do not have per resource fences. So when you destroy a resource, you can't reclaim the memory immediately. We do not actually say, oh yeah, there should be a fence for resource, and there's some queue of fences that you have to check, and then you delete, et cetera, et cetera, et cetera. There's a fence per frame, and then we say if a resource was deleted in frame 5, it most likely was actually used by the commands submitted in frame 5 or 4. This is mostly true for us. And we will just delete it when frame 5 is done executing on GPU, right? So we have pretty high granularity for resource destruction, and it works fine for us. We use this for every single thing that you would have to destroy. The other thing that we do is we do not track layouts for images. So in Vulkan, you have to transition images between different layouts. So you are starting to render to this image that's a render target, okay. You have to go to like color attachment optimal, then you have to go out of this, etc. So we do this, obviously, you can't not do that. But the begin end pass boundaries that we have turn out to be almost perfect for almost all barriers that you need per frame. So we don't track layouts. We just know that this resource is supposed to be in this layout before an operation and in a different layout after the operation. The case where it does not work is compute, where we do have to track, but we don't ship any compute code right now, and the development prototypes that we have like tens of dispatches per frame, so it's not really a big deal. The other really big thing is, so we are doing dynamic descriptor updates, right? You have to be smart about how you do that. So first, you should absolutely use dynamic uniform buffers. So this cuts our allocation of descriptor sets in like half or maybe 3 times or whatever, and it makes some other things faster. Another thing that you can use is when you switch pipeline states, you don't have to technically rebind everything. You should read Vulkan spec. In general, you have to read Vulkan spec when you do Vulkan development. But specifically, there's a part of it that tells you when the pipeline layout is compatible to another pipeline layout, and we use these rules, and they do work on all drivers that we have tested. So this is all fine. And the last part is just profile every single line of your code, optimize things that you think should or can be optimized. There's a lot of small things that we did here. Like, turns out cache misses in your code are important. They were never actually important in this portion of the code because there was the GL driver that takes like 10,000 cycles per draw call or whatever it is, and it's just, who cares? There's 1 more cache miss, 2 more cache misses, nobody notices it. With Vulkan, you do notice. The other thing is that when you do a Vulkan call, you go through a dispatch table in the loader, and you can optimize some of this out, and we do so, and there are some gains because of this. There's a library on GitHub that we published that does this for you. It's pretty easy to integrate. And this is, roughly speaking, how we ported the C++ parts. So I have good news and bad news. So the good news is this. There is this comment that I heard often before that, well, the drivers are really, really well optimized. You cannot beat the driver, or you can beat the driver, but it will take you so much time that you might as well not do this. So for us, note, we did not have to reimagine our entire renderer around Vulkan, right? This is a backend. This is just, we have this rendering abstraction. It already has like 5 implementations. Now it has a 6th one. And we are seeing dramatic benefits. So on mobile, we are seeing like 2 to 3x benefits in terms of time that it takes us to dispatch the scene, to send the scene to the GPU. On desktop, we are seeing large benefits. What's interesting on desktop is, so when you use DX11, on both NVIDIA and AMD, there is a driver thread. And the only thing your code is supposed to be doing is like buffering the commands for the driver thread to pick up. And our Vulkan code is like faster than that, even though the DX11 part of this doesn't actually do work. It just forwards everything. And the Vulkan part does not use the driver thread. So this has been really good. The PowerVR number here is a bit suspect, but I think what happens here is the thermal throttling, which is on this workload, you know, the device just cannot sustain it on OpenGL, so it has the thermal throttle and then drops the clocks, etc. One other thing that's interesting to note is this is not a micro benchmark. This is time that it takes the render thread to start from here's your camera, go. So it does the frustum calling, the scene graph traversal, the particle simulation, I think, like draw call dispatch, et cetera, et cetera, et cetera. So this is end-to-end, right? So this is really good because this means that you can get even faster by, for example, optimizing the parts that do not depend on Vulkan. And this is all single core. We have experiments with multi-core, but we didn't ship anything yet. All right, so here's the problem with Vulkan on Android. So here's the good news first. 17% of Android users can use Vulkan. This is great. If people in the audience are not familiar with Android graphics, 25% of our audience is OpenGLS 2. So 17% is great. I mean, we'll take what we can get. So the bad news is that almost all of these users come from Android 7.0, which is when the Vulkan support became official. You see 6.0 users as well. I think this is mostly Samsung devices that support Vulkan on Android 6. So 7.0 is conveniently, it has shipped like a few months after the Vulkan 1.0 spec became public. So we are dealing with early drivers here. So really quickly, a couple of things that we have ran into. So synchronization in Vulkan is challenging. Fred and Ina will talk a bit more about this, and they have great examples. We have ran into one specific thing that they will talk about, because probably everybody runs into this. And I mean, the short version is Vulkan synchronization is hard. You probably don't have an accurate model, unless you're Tobias Hector, of how exactly it works. We have found bugs in, like there was a bug in ARM Vulkan SDK that is open source that we have reported and it has been fixed with synchronization, where the sample just wasn't doing the right thing, right? So the corollary of the rule 1 is the rule 2, where you know your barrier code just doesn't do what you think it does. So the big problem right now is there is no validation for the correctness of synchronization. There are validation issues for some things, but largely speaking, it's not fully doing what it should be doing. So 2 important links that you might want to use. So one is on Kronos Group Vulkan docs repository. There's a page of examples of, I'm doing this specific thing, what kind of barrier setup should I use? So this helped us understand some peculiarities a bit better. And also there's a library simple Vulkan synchronization that Tobias Hector wrote, who is the only person who understands Vulkan barriers, which models a DX12-like resource state model on top of Vulkan barriers, which is a bit easier to wrap your head around. It's easier to say I'm transitioning this resource from state A to state B, because the library figures out all of these stages and masks and whatnot for you. So that quick thing that we ran into, VK-free command buffers can not free memory. It is by design. So when you create a command buffer and it comes out of a command pool that it is created with default flags, you can call VK free command buffers. It will never free memory. What will free memory is VK reset command pool. So we had a memory, and this is of course only on 1 out of like 6 vendors that we support. So there was a memory leak where the command pools just weren't freed. So use reset command pool or reset command buffer. And also there are complications with threading, where the API doesn't make it super easy for you to do certain things, but I will not go into that because we haven't actually shipped this on Android. So, all right, so now quick fun part. We have hit a bunch of bugs in both the shader compiler on the driver side and the actual like Vulkan driver. They are listed here. Some of these are interesting. The last one was cute, like our UI shader that's like 5 instructions had a branch in it because of reasons, and the driver did not compile the branch correctly. And in general, it's been a bit painful. So most of these only surface with HLSL pipeline or SperVopt. So this has been more painful for us in terms of the future ongoing development. The way we work around these is usually either we figure out how to transform this per V offline to not trigger the bug, or we change the shader, which we don't like to do, but we did it a couple of times to work around this stuff. So we have hit a lot of driver bugs. Wait, I think I promised Alan to tell that Android drivers are perfect. Sorry. So a lot of these are kind of simple to understand, which was great. We didn't hit a lot of performance bugs. It's mostly behavior bugs. And they're pretty easy. Like when you are doing MIP map generation on a cube map, the natural thing to do is to call vk-cmd blit image and tell it, well, I have 6 faces. Blitz 6 faces. Well, it turns out the driver ignores the number of faces to blitz, so just blitz the first one. But the workaround is obvious, right? You just call the function 6 times. It's not hard to understand. There are some things that were fun, like on one of the devices, we just had to blacklist it because it swapped red and blue in the final output. And we could hack our shader to swap red and blue, but we don't like these kinds of workaround because they're very fragile. So for most of these, we found workarounds in our code that were not particularly performance sensitive. For those where we couldn't find workarounds like this, we just blacklisted the driver. Speaking of, so speaking of driver bugs, what do you do when you hit a driver bug? Well, first you find out what it is, you try to work around this? Well, no. So first thing you should do is report it. Where do you report it? So you have several reasonable options. You can talk to the platform holder. So we worked with Samsung a lot on this stuff. If you go to the link, they have a game program where they help game developers deal with this. Google has a public issue tracker. I'm not sure how well it works yet, but we have reported several bugs, and I've been told they're being fixed. And the most important thing, though, is report the bug to the conformance testing suite. So there's a public GitHub repository. You can file a GitHub issue there, and you can say, well, on this driver, if you do this, this does not work. Can you please add a conformance test? This does not help you immediately, but it helps the ecosystem, because this means that in like 3 years, 4 years, 5 years, other people will, okay, maybe sooner, other people will not have this problem anymore. So this is great. So you have seen the Android stats. The Android stats mean you have to work around bugs. You can't just say, oh, the future driver will fix the problem. So how do you do that? How do you find out if the driver has a bug? So these are the 4 things that the driver tells you right now. The API version we didn't find to be useful, or rather, if it's less than 1.0, do not try Vulkan. It's just pointless. If it's greater than 1.0, it doesn't really matter. Driver version is very painful to work with. Mobile drivers like to put things like the binary hash of the executable, and then we talk to the vendor and we're like, this is the driver version that we hit this bug on, and they're like, we don't know what it means. And vendor ID, did you know that Intel's vendor ID is 8086 in hex? Anyway, so device ID is not useful for us because most of the bugs that we have seen are in drivers, not in devices. So we right now use a combination mostly of vendor ID and just Android ABI version. Like we say, we have seen this bug on Android 7 and 7.1. Dear God, please let it be fixed in Android 8. This actually works. This has been the best thing that we did so far. There is some work around making this better, so I'm hoping that in the future this will improve. And when we want to blacklist a specific device, we just blacklist the entire device. Like, we just use the Android, like the model name or whatever. This is easy because when a user reports a bug, we ask them what device it's on, and then we can blacklist it, and then we can figure out what the problem is, and then re-whitelist it if possible. Bug reporting guide, I briefly talked about this already. If you found a bug in your code and it's not validated right now, consider reporting a bug to loaders and validation layers, once again, to help other people in the future. And for all of the shader stuff, if you found a bug in a shader tool X, please report a bug to the shader tool X's GitHub repository. So the good news that I promised was that we did ship on Vulkan. It does work. It is much faster than OpenGL. There aren't too many maintenance issues with it, or rather not more than there are with OpenGL. The bad news is it requires high pain tolerance. And please file bugs on things that you find to make Vulkan better. Thank you.
Hello, everyone. So I'm Frederick, working for Samsung UK office as a DevTech engineer. Ine Kim will be jointly speaking with me. She's also a DevTech engineer, but working in the office based in Suwon. So I'll go through our experience working with pipeline barriers, which, as Arseny said, has been one of the biggest pain points, I think, for most developers. So it's a short session, so I'll just go through a simple example and try to see how pipeline barriers make sense in this example. Along with that, I'll give a case study where we made use of pipeline barriers to optimize some performance issues, and along with that, fix some artifacts and so forth. Then afterwards, Ine will cover the loading time improvements, specifically related to pipeline caches and pipeline derivatives. OK, so what do we do and who are we? So as part of the Galaxy Game Dev program, announced at SDC 2016, our job is to promote the use of Vulkan on Android, but most of all, support game developers targeting Android devices. So we want to build a better Android game ecosystem, and the way we do that is by supporting game developers all around the world with various issues, both on-site and remotely. So before starting, I want to say that our results are based on our experience working with the Galaxy S7 and Galaxy S8 devices, using the ARM Mali and Qualcomm Adreno GPUs. So the games we'll be focusing on today are Blade 2 by Action Square, Alliance X Empire, known as Axe by Nexon Red, and Final Fantasy 15 by Square Enix. and also Lineage2 by Netmarble. Okay, so I've given you an introduction of what we do, and I'll go with an introduction about pipeline barriers. So as you all know, Vulkan is a complicated graphics API. There's a lot of bookkeeping to do, having to track resources, manage device memory, and all of this bookkeeping is basically what the OpenGL drivers are currently doing. But what Vulkan does is it gives you more control over these things, and at the end I'll go through how this control has actually helped us optimize the games we've worked on. So on the slide here, you can see I've got some of the parameters I'll touch on throughout the examples, and I'll go through it now. Okay, so copying data to an image is conceptually a simple task. So that's why I'm actually covering this. But first off, images in Vulkan are created with a specific tiling arrangement. So there's linear tiling, which is basically text cells being laid out in row major order, possibly with some padding on each row, and it makes it possible to write to it via the host. And then there's also optimal tiling, which is basically an implementation-dependent arrangement. And what it enables is more optimal device memory access. So in this example, we'll go with optimal tiling. So on top of tiling, you also have, well, the images require valid memory layout, image layout. So as Arseny touched on, in Vulkan, you have to transition an image based on the usage, and the layout is specific to how the image will be used. So to be able to actually transition to the layout you want to use, you have to use a pipeline barrier, and that's exactly what I'll cover for this specific example. The other thing related to layouts, as part of image creation, you have two options. So you have the undefined layout, which is the only thing you can go with when it comes to optimal tiling, or you have pre-initialized, but that only makes sense with linear tiling. Okay, so I'll go through the kind of fields we have to pass to the pipeline barrier when it comes to copying data to an image. So I said the initial layout will be undefined. So when it comes to actually transferring data to an image via the device, you have to transition the image from an undefined layout to a transfer layout, which is shown here as transfer destination optimal, since we also have to tell the driver how the image will be used. And in this case, it will be used as a destination of a copy. So the other thing we also want to take care of is the execution and memory dependencies. We want to make sure that these transitions happen in a well-defined order, and this is exactly where the source stage mask and destination stage mask come in play. There's a handful of these in the Vulkan spec, but I'm only going to cover the ones that make sense in this example. So the way it works is you wait for the pipeline stage in source stage mask, and in our case, this is specified as top of pipe, since we don't need to wait on the image. It's freshly allocated. It's garbage data. We just want the copy to happen right now. And then when the stage in source stage mask completes, you basically unblock the stage in destination stage mask, or rather the driver or implementation unblocks that. And that means that the transfer stage can start executing, which is basically a conceptual stage where the copy occurs. So given that our source stage is top of pipe, this gets done, copy occurs, and that's pretty much what's happening. The other thing we really want to do here is also, as I said, add memory barriers. So we want to specify the type of access that occurs in the source stage and the type of access that occurs in the destination stage. And this is basically what the source access mask and destination access mask help you do. So I set source access mask to 0, since there's not going to be any relevant access. It's garbage data. We don't care about that. But then you also have to specify the type of access you're doing as you're copying data to the image, which in our case is a transfer write, as we're copying data to an image as a destination. Okay, so let's assume we've done the copy, and we added the relevant barriers. Now let's assume we want to sample from the same image. And then as I explained before, lots of things to keep in mind in Vulkan. Have to make sure that we transition the image to the correct layout before actually sampling. But now that we have a copy that we scheduled as well, we have to make sure that the copy actually completes before we transition and before we sample. So to ensure correctness, we add another pipeline barrier. We define the relevant dependencies. And what we want to do in our case is transition our image from a transfer destination optimal, which is the old layout, to a shader read-only optimal, which is the layout you need as you're sampling an image. So we also want to specify the execution dependencies, as I touched on before. So we specify which stage we want to wait on. And in our case, this is the transfer stage, as can be seen on the slide. That's where the copy occurs. And then once that stage completes, then we can unblock the fragment stage and actually do our sampling. We add the relevant barriers as well. So basically, what we were doing in the transfer stage, we were doing a transfer write. What we're going to do now in the shader stage, we're doing a read. OK, the thing I want to say before I move to subpass dependencies is that the type of transition that you're doing with copying isn't just about copying. So essentially, for any kind of usage your resource will go through, you always have to change the layout, transition, all sorts of things. So this also applies to when you're rendering and presenting. For this example, I'm going to cover subpass dependencies, which is specifically related to when you render to an image and then present it or give it to the presentation engine. So let's assume in this case that it's a completely different image. I've claimed it from the WSI swap chain, which I won't go through since I'm not a swap chain expert. So let's assume we're rendering something super simple to it, a triangle, and then we give that back to the presentation engine. So we can do that using a pipeline barrier, similar to the previous example, but different stages, different layouts, and different memory access, depending on the usage. But it's more efficient to do it as part of a render pass instance. So what the render pass enables us to do is specify the image layouts, or the layout the image should transition to for each subpass, but then also help you specify the layouts that you want to transition to as the render pass ends. So then the question here, and I've added that here, if it's more efficient than a pipeline barrier, then why did I use that in the previous example? And the reason for that is because every function in Vulkan have a render pass scope, which essentially tells you whether you can use the function within the render pass instance or outside of it. And given that our copy in the previous example was outside the render pass instance, your only option is to use a pipeline barrier. So when you're doing something within a render pass, subpass dependencies are the way to go. So on this slide, these are the relevant parameters when it comes to subpass dependency. The VK image layout here is the layout that the image transitions to for each subpass. And then you've got the VK attachment description. Initial layout is the layout before the render pass, and then the final layout is the layout that it automatically gets transitioned to at the end of the render pass. You have to take into account the execution and memory dependencies, similar to pipeline barriers, and this is where the VK subpass dependency structure comes in play. So, as explained before, lots of transitions to do, lots of things to keep in mind. Let's assume there's no off-screen rendering, there's no reading back data, it's just one subpass, very simple. We're just rendering and presenting. So we want to transition our image to a renderable layout at the beginning of the render pass, which happens as the subpass executes. And then at the end of the render pass instance, as we give it back to the presentation engine, we want to transition it to present source KHR, which is the layout you want. So before we actually transition to a renderable layout, we also want to make sure that the presentation engine is done reading from the image before that. And that's exactly what the subpass dependencies help us with. They help us define the operations we need to wait on, but then also define which ones should start after these waited on operations complete. So on the slide here, I'm showing the implicit subpass dependency, which is defined by the Vulkan spec. And this is essentially a subpass dependency that's injected implicitly. So unfortunately, this isn't good for us, since nothing gets blocked. So basically, top of pipe is being specified here. So we want something that actually transitions at the right time. And I'll also go through what each field means. So source subpass basically defines the subpass index of the first subpass in the dependency. Subpass external basically means that we are synchronizing against commands submitting before the render pass instance. Destination subpass is similar, but that's the second subpass in dependency. Subpass external means our synchronization scope includes commands submitting after our render pass instance. And then the other parameters like source stage mask, destination stage mask, and the access mask, they're similar to pipeline barriers, which I've touched on before. But the final one, which is, from my point of view, given that I work for Samsung, the most interesting one, is the VK dependency flags, which basically only has one field called dependency by region. And that's really useful for tilers. So it's not useful in this use case. It only makes sense when you're having something like multipass, where you have two subpasses. So that basically what this does is it enables you to say that the synchronization scope is per pixel rather than frame buffer global, so that when your second subpass is executing, you're not waiting for all the pixels in the previous subpass to complete. Since you would never be able to access that in a tiler, the synchronization scope is per pixel. But in this example, we won't make use of that since there's no multipass. OK, so As I said, you have to add your own subpass dependency for correctness. So we change the subpass dependency here. And before actually explaining why I chose this stage, I want to sort of explain a bit more about queue submission. So as part of queue submission, you define a set of wait semaphores to be signaled, and these get signaled when the presentation engine is done reading for the image. This is so that rendering can start. As part of this wait semaphore, you also have to say which pipeline stages need to be blocked. And obviously, the most efficient one is the color writing stage, which is color attachment output bits. And what this means is that in theory, implementations have the opportunity to start executing the vertex and fragment stage, and then only start rendering once the semaphore is signaled. So in our case, the execution dependency is guaranteed by the semaphore submitted as part of VK submit info. And the reason we have a subpass dependency here is just to time the layout transitions at the correct time, just to make sure that we're actually transitioning to a renderable layouts as we are rendering and not before. So source access mask, I set it to 0 since we're doing a write after read dependency. So destination access mask is set to read and write bits. So I added that since it's pretty common, but the read bit generally isn't needed, except if you're doing blending, so you're reading from the attachment as well. In this example, write bit makes sense. OK, that's a lot out of the way. As I said, you also have to specify the final layouts, and that's a second subpass dependency. There is an implicit one as well, which defines the synchronization scope between the render pass and after that. So that's why you have subpass external in the destination subpass. So in our case, we want to transition to present source KHR, which is the layout the presentation engine needs. And so this implicit subpass dependency is fine in terms of execution dependency, because it defines that the transition happens after all work is done, aka bottom of pipe. And since we signal a semaphore in order to present, it's the same thing as before, but except this semaphore basically says to the presentation engine, hey, wait for my image to be ready before you can actually present it. You can add your own subpass dependency if you want. So it depends on the usage. So one example is right here, but it's not necessary since the implicit post-render pass dependency is fine. OK, so now that I've got that out of the way, I'll go through some of the real cases we went through with pipeline barriers. And this case is for Lineage2 Revolution by Netmarble. So this was a case where an image was being transitioned to a readable state for it to be sampled by the fragment shader in another pass. And we've noticed that they were using wrong stage masks, which basically led to some pretty bad pipeline bubbles, as we could see in some of the tools. So as we fixed that, this gave us a huge boost in performance. So basically, it was as follows. Image was being rendered to, and then we would sample from it. So we transitioned to a readable state. And in that case, what we want to do is wait on the color writing stage. And when that completes, we unblock the fragment stage and actually start doing the sampling. So as you can see on the slide here, so this is DS5 Streamline. There are 3 images, and the gray part is just a timeline size. So we basically measured the original GLES build, the Vulkan build with the incorrect barrier stages, and a Vulkan optimized build. So for OpenGLES, our initial evaluation was 20 milliseconds for frame time. And then with Vulkan, as we ported it, but didn't actually do any for optimizations, we got 24 milliseconds, which basically means that it increased by 3.4 milliseconds. After optimizing all the barrier stuff, reducing pipeline bubbles, and optimizing as much as we can, so even outside of the scope of pipeline barriers, we got 12.4 milliseconds, which gave us a gain of 8 milliseconds. So this game is Final Fantasy XV Pocket Edition by Square Enix. So we provided on-site support to Square Enix and Summertime Studio in Okinawa, Japan. So this was an on-site support with teams from Samsung Suwon, Samsung UK, and Samsung Ukraine. So it's a Unity-based game, and the kind of optimizations we've applied include pipeline barrier batching, fixing the stage masks, but also fixing the content and trying to optimize it as much as we can. So before, at the beginning, I touched on how low-level Vulkan is and the amount of access you have as a developer. So from our point of view, we believe that due to this low-level access, that's how we were able to reduce the frame time as we have here, because we were actually able to say for each resource how we want them to be synchronized and in which stage. So that's all for me today. I'll hand over to Kim, who's also a DevTech engineer, and she'll be talking about loading times, specifically about pipeline caches and pipeline derivatives.
Hi, I'm Kim, and I'd like to start to talk about the tip on how to improve loading time related to the pipeline cache and derivatives on mobile device with Vulkan. We have this progress bar when loading time, and it takes a while. We need to load game data while initializing and during the scene transition. As you all know, Vulkan needs to create pipelines for loading the data, which is really important. For creating pipeline, we need a lot of information like shader stage, vertex, viewport, rasterization, depth, color blend, layout, render paths, etc. For this reason, creating costs too expensive. In my presentation, I'm going to talk about this creation costs of graphics pipeline, especially pipeline cache and derivatives. I've already said pipeline cost is too expensive, and I just briefly mentioned about how to use pipeline cache. Calling VK create a graphics pipeline with pipeline cache effective for performance. After creation pipeline cache, it can save to SD card. And when using the same pipeline, this saved cache can be used instead of creating new pipeline. As you can see, this screenshot is displayed to mobile, and we provide on-site support to Action Square. This game is action RPG, so when loading battle scene, it takes time as the game needs to create all the pipeline it needs to use. After it doesn't create anymore, just play the game. Let's talk about this table. This data on the table is time for executed all of VK create pipeline when loading scene on Blade to mobile. In this case, one scene needs over 300 pipelines, and creating pipeline takes 30 milliseconds average without pipeline cache. How about with pipeline cache? It takes less than 1 millisecond. As you can see, second loading has big difference with using pipeline cache. It improved from 9 seconds to 0.2 seconds. Also, first loading time using pipeline cache has improved from about 9 seconds to 5.5 seconds. It's better than before. Let's move to the next point for improved loading speed with pipeline derivatives. Pipeline derivatives is a child pipeline created from a parent's pipeline. If you use pipeline derivatives, cost of creation will reduce when child pipeline has same commonality with parent's pipeline. But in real game case, it may not be helpful for optimize the performance because it depends on the shader situation. And benefit of using pipeline derivatives vary between GPU architectures. GPU architecture may not support this function, but no make bad performance, it doesn't working with derivatives. So how to use pipeline derivatives? If setting the flag to disable optimization bit in the VK pipeline create import structure, so it means they don't use pipeline derivatives. For using pipeline derivatives, set the allow derivative bit, and after creation this pipeline, save to handle or index. This is the parent pipeline. And child pipeline, set the derivative bit and base pipeline handle or index, they need to exist handle or index for derivatives. So how much performance improvement can we get through the pipeline derivatives? This table is for executed all of the VK graphics pipeline with 24 pipelines at sample application on Galaxy S7 Snapdragon. And shader 1 to 3 are different. As you can see, there's a big difference between the result with pipeline derivatives and the result without derivatives. Until this slide, I have to talk about pipeline cache and derivatives. So what do you think about difference with cache and derivatives? Difference is how to save and load the pipeline and how can find that. Pipeline cache save and read from the SD card, and pipeline derivatives save pipeline handle or index on runtime. When is the program use only one pipeline and reuse it again and again, then pipeline derivative is faster than cache because the time for reading or writing from SD card. And handle for pipeline derivative is so small and already know it, so it doesn't need to search. As a result of our experiment, each time for creation time when it used pipeline derivatives or pipeline cache. Pipeline derivatives about 3 times faster. But the total creating time result, pipeline cache can reuse when all of reloading, but pipeline derivatives can reuse when specific case, like having the same parents, that make different performance. Let me show you one of the results of our experiment. This screenshot is game Alliance X Empire. I call it the X, and we provide on-site support to Nexenra Studio. This was a camp with terms from Suwon and Ukraine, and also provide remote support from UK. And this data by our experiment for this topic, X has the open world, so it need to load data that need to enter to the game world. For this case, loading time is time for launching game until enter to the game world and see like this screenshot. This game have about 300 shaders, but at this scene, create about 60 pipeline and 60 shaders. Let's check the result. And this graph is based on the table, and I will talk about these 2 red boxes. First red boxes at the upper side is result of pipeline derivatives between nothing and only pipeline derivatives used. Pipeline derivatives can give the loading performance improvement, and it gets worse than sample case. Because different performance made by how many child pipeline that derive from same parents. As you also can see the second red box at below side, using pipeline derivatives with pipeline cache, it have a little difference with using pipeline cache after second loading time. In this case, using pipeline cache after second load make difference with pipeline cache and derivatives. Basically, pipeline cache is fast after second load, but pipeline derivatives can make little more improvement. When reuse the pipeline, if you can use pipeline derivatives with cache, don't need to access the SD card because already have handle, so use it. That's why this data can show you the makeup improvement. In conclusion of this experiment, pipeline cache is necessary for improved loading speed. If you can use, have to use. But if you couldn't use the pipeline cache, so pipeline derivatives can be the second choice. And if you need more improvement loading speed, you could consider using pipeline cache and derivatives both. This is the end of the presentation, and if you'd like more information about Galaxy Game Dev, then here is the link to the developer page. And you could also contact me or Frederick or Game Dev email. And I'd like to thank you for your kind attention today. If anyone has any question, please feel free to ask now, and we will do our best to answer.
Hi. Any power consumption data or regarding OpenGL versus Vulkan on the mobile devices?
So you're asking about difference between OpenGL, yes, and Vulkan?
Yeah, savings on power consumption.
So there was the slide I was going through. Let me go back to it, which was for Final Fantasy. No. God. Okay, so basically the DS5 streamlined output I was showing. So this, basically the first one on top shows the frame time for OpenGL ES, and then the ones below show with Vulkan, without our optimizations, and then after that with the optimizations. Does that answer your question?
Yeah, no, that's actually frame time. I'm talking about like power consumption reduction, like battery consumption reduction,
so,
regarding Vulkan and OpenGL.
Yeah, we have seen that for some games we worked on,
yeah.
But we don't have data now.
Okay.
But so basically, Vulkan gives you the choice to target whatever you want. Either it's the frame time or the power perspective, but from our side, we don't have data. Maybe you do?
So we don't really measure this explicitly, but these concepts are a bit interlinked. So if you are targeting 30 Hz frame time and your entire frame takes you like 30 milliseconds to render, and then with Vulkan you cut it in half, then this is your power savings, because then you can just not do anything, or you could target a 60 Hz game with a similar power consumption, or you could just not do anything for the remaining 15 milliseconds. So we don't really have precise data. It's better on some of the things that we do where we care about battery consumption, but it should be, you should have more freedom essentially depending on if you're GPU bound or CPU bound.
Yeah, I would imagine you get a lot of power consumption savings. It's just that sometimes it's not linear, like on the, like on the frame time is not linearly, no linear relation with power consumption. So that's one. But yeah, thanks for feedback.
It's going to be a tough one.
Hi, so this is not really a question. I was just gonna have another answer to this. We actually presented numbers on this in 2016 or 2017 about especially CPU power savings can be 50% reduced. Just the fact that it's the rule of thumb that it's 3x reduction in CPU time, and that really translates to roughly 50% CPU power savings, assuming your engine is not spending a lot of effort doing other things. And on GPU side, it depends. Again, if you can improve frame times, definitely. But yeah, I'd rather bank on the CPU power savings.
All right, thank you everybody, and we'll hang out here for a bit if anybody has questions that they do not want to ask while we're on stage.